Welcome. Welcome to the 2021 edition of the Summer School in Terahertz Technologies and Applications. My name is Idelfonso Tafur Monroy, and I'm professor in terahertz systems at the Eindhoven University of Technology. We are in Eindhoven, the Netherlands, from where we have the honor to welcome you, participating from all parts of the world, to an exciting week of learning about the field of terahertz technologies. As expected from the summer school, we're going to do this together, have fun learning, and we will discover what we can do with terahertz for solving societal challenges, such as in healthcare and agri-food. These are two examples that we just choose to mention it. And by doing so, I'm sure we will make new acquaintances and new friends too. This year, our online edition is a special event. This is the 30th summer school in a row of the series of the International Summer School. So this event has a long history and tradition. It was started with a goal in mind, particularly to allow researchers, students, professors from different disciplines, such as quantum electronics, microwave photonics, terahertz, and other related areas, to learn about their applications to real-world problems, while not just crossing the scientific discipline borders, but also to cross the borders of geography and cultural. This goal remains equally important today as it was 30 years ago. Education, research, and entrepreneurship is people's work. It's passion. It's about engagement to contribute to society with technological solutions to important challenges, and it is best done by combining talents and looking at those same challenges from different perspectives. It remains equally timely to remind ourselves of the importance of safeguarding the values of scientific judgments and facts, and to nurture inclusiveness and intellectual diversity. We at the Eindhoven University of Technology are very honored to be hosting this 30th edition of the Summer School in Terahertz Technologies and Applications. The program for this week includes keynote lectures from renowned professors in the field. Our program is completed and complemented by lectures given by experts from industry and colleague professors from several universities. We are covering the fundamentals of terahertz science, fundamentals of electronics, photonics, and circuit integration for terahertz devices and systems. We are covering important applications of terahertz in wireless data communication, spectroscopy, metrology, imaging, and microscopy. A very important element of our summer school is the work students perform together to solve a challenge. A challenge is an assignment related to a real problem in industry or technology, a challenge that is timely and waiting to be cracked. We are looking forward to the presentation of the solutions you will come up with to those 10 challenges posed this year. Those topics range from virus detection and blood coagulation monitoring using terahertz waves, up to how to realize those solutions on a compact chip. Our summer school team has prepared a series of online tours to several terahertz and nanotechnology facilities. Those tours will introduce you to what is possible at those unique laboratories. You will learn about what activities are going on and how to become part of those too. Our industry sponsors have prepared an online booth. You are invited to visit. There you will interact with experts, learn about their products and development, and also to see and learn about the challenges they also are facing, and also become part of them too. Finally, our team has prepared for you an interactive social program and fun interactive breaks. Now, to continue our welcoming and opening session, I would like to invite Professor Harmon Roskos, who is going to talk about the importance, about the history, and the prospects of this exciting and important knowledge area that is terahertz science and technology. Professor Roskos, the podium is yours. Yes, welcome, Professor Roskos. The podium is yours.
Can you hear me actually? Because
yes, we do.
yes, hello. Can you hear me?
Yes, please, Professor Roskos,
no.
the podium is yours.
Okay, you have deactivated the sharing. Can you activate the screen sharing? It's still
Okay, we are
deactivated.
working on it. We hear you, so we're activating now. So I think you are ready to go, and thank you for your patience.
Okay, now let's see. Actually, you should be able to see my screen now. Do you see it in presenter mode?
It's good now. I hear that everything
Okay,
is ready.
okay, let's get started. Actually, I could not hear Professor Monroy's speech. Somehow the sound in the other system didn't work properly in my case. So this is why I hope you can hear me. Okay, so let me delve into my task. I understood my task at giving you some introductory remarks on the status and potential of TTASS technology. And I will see what I can do in a short time that I have to give you a feeling about this status from my perspective. Well, we are dealing with the TTASS technologies, right? This is essentially everything that is in the range from 100 gigahertz to 300 gigahertz, which is the delimiter between the millimeter and submillimeter waves. And submillimeter waves are often considered the equivalent of terahertz waves, all the way up to 10 terahertz, right? So all technologies that relate to this, whether electronic, optoelectronic, photonic, be devices, systems, applications, and be the applications scientific, industrial, or consumer related, belong to these kind of terahertz technologies. Now, everybody of you, or most of you, know this kind of picture where the terahertz frequency range, as specified up there, is in the middle of the electromagnetic spectrum, bounded by the microwaves on the low frequency side and infrared radiation on the high frequency side. Now, there are in this range fundamental challenges, and what I would like to emphasize is, right, the microwave land is beautiful and mature, and the VCR land is also beautiful and mature. But for a long time, at least when I started, not so much these days anymore, the TTASS range was a barren land, like a desert in between these well-developed regions. And I will address this point in the following. Well, there's fundamental reasons for this challenge, for the problems, why it was a desert for so long. This is, as one sees already, right, that the sources and detectors that are used on either side of the TTASS radiation are different ones. Well, we all know, right, that let's say in terms of sources, we have lasers on the infrared and visible side. Well, why is it possible? Simply because transition energies, h bar omega, are larger than the 25 millielectron volts thermal energy at room temperature, and 25 millielectron volt thermal energy, this is about 6 terahertz. So above that, lasers are easy to make, whereas in the microwaves regions, no lasers exist. In the terahertz range, in between, there is some. Well, on the other hand, the microwave region has efficient electronic oscillators, and you will not find them so efficiently here at the high frequency side. Why? Well, even if you can run them and you have the same kind of like energy density in these devices, you will not have much power, because simply resonance conditions with these smaller wavelengths require that your structures are small and the volume of your sample is small, so you don't get out so much power. On the detector side, we have a few photon detectors on the high frequency side, but because of you need many photons to overcome the noise at room temperature at least, there is no room temperature single or few photon devices detectors available here on the low frequency side. So we're just in a boundary region here between these two different worlds and have to find ways to cope with this. And the clearest or most popular expression of this challenge is this terahertz gap plot with the output power over the frequency with the reduced power available in the terahertz range. Well, this gap is slowly filling up, but still not, there's still this gradient to both sides in terms of power. Well, but there's also advantages to be in between, because one can borrow technologies from either side. For example, we have emitters and detectors that are either optoelectronic or all electronic. We can adopt wave propagation concepts from free space optics. We can build modulators based on this, what is available in this spectral range. On the other hand, we can exploit the phases of waves easily, as with microwaves, which is not so easily possible in the optical range. And one can adopt imaging modalities, for example, from radar, that are not available in a visible range. Well, where I want to come to applications. TTASS radiation is of high importance in fundamental research in physics and material sciences. And this has not only for that reason, but more strongly to do with the fact that there's many materials and many new materials in phenomena that have so-called elementary excitations in the milli-electron volt energy range. And a milli-electron volt, 4 milli-electron volt, is 1 terahertz. So we're just in that region where a lot of the interesting action happens in these materials. I don't want to go through this list of typical materials and phenomena, where I also plotted here in brackets application ideas that people have with these materials and phenomena. Just want to point out the 2D materials derived from discovery of graphene, extended nowadays to transition metal dihydrogenide, where you can also make heterostructures of this whole family of materials, which opens a completely new tool set for making new kind of devices and functionalities. For example, Moray superlattices, where for the first time one has been able to predict superconductivity, which indeed then was observed as predicted. But where are the real world applications? So as I said, right, in spectroscopy, terahertz is strong and cannot be overlooked. There exist applications, right? We know that the identification of so-called polymorphs in pharmaceutical compounds is extremely successfully done with terahertz radiation. Polymorphy is that a molecule with a certain sum formula can have arrangements of the atoms in different ways, and this leads, at least in a crystalline phase, to different terahertz absorption spectra, which allow to identify them. Another application that is in the world, and I know companies, for example, a Canadian company that fully lives on that basis, time domain systems are used for the characterization of car paint, the thickness determination, even in for samples in the factories. Wafer inspection, connectivity measurements is in the market, and as said, in the lab and space applications, terahertz is strong. And then the other thing is also that technologies are certainly coming. For example, wireless communications will also be a big topic in the summer school. Now, gas sensing of environmentally relevant gases is also coming as a technology in the market. Now, there's many possibles, right? Radar-like sensing, imaging in robotics and autonomous vehicles is one that I would bet on, and medical, where I'm not quite so certain of. Now, however, in spite of all this potential, one has to say, right, that until now, there's not yet a large mature market that has been developed outside of the scientific ones. And what are the obstacles, and what then is also the potential that you as students will have for your work? Well, let me address this perhaps from a point of an example, because I think this is something that you students, especially students, should also think about during the summer school. What makes a technology actually successful? What should one put what should one look for if one wants to make the technology successful? Let me give you an example of a successful story and one that was not quite as successful as it could. For example, not too long ago, the Munich company Rohde & Schwarz developed a security imaging system in a portal-like fashion that you now find on many airports. It's actually built on emitters and on thousands and detectors and emitters in such panels as shown here on the left, uses modern radar technologies built in a sub-100 gigahertz range. And the image quality is so good, right, that this actually makes this product so successful that it is fully in the market. On the other hand, other applications like this one that I'm showing here for the detection of pipe seals was not so successful. This was a company that was spun out from my group. Or with the same kind of systems, they were able to look through walls. For example, here, this is a damage assessment of walls in Japan, where they use a lot of such tiles on the walls after an earthquake, and what can see is the losing of adhesive contact of the tiles to the walls here, where the white is gone, right? There the contact has been lost. Or actually 3D imaging in terms of this tomography that is shown here. This all did not make it really into the market. Well, what's the reason? Well, one reason certainly is this is slow techniques. It takes a long time to map here the wall or to take the 3D images. It's a single pixel emitter and detector, and it's also expensive, cost even the active source alone was tens of thousands of euros. So typical reasons for the lack of success in the market is too slow, too expensive, and not enough added value to the customer versus competing technologies. Now this is a static picture, right? But there's also some dynamics in these kind of things. And one of them is the hype cycle that has to be taken into account. Essentially what one means by this, the kind of expectations that arise if a technology is developed, right? Typically after some discovery, the expectation rises until a peak is reached, and clearly expectations are inflated. Then the hype falls down, people lose expectations, it's a trough of disillusionment, and often it's also a death for, let's say, small companies whose investors give up. But then typically people realize why they had the problems or why they used what kind of wrong application perhaps they selected. This is then the slope of enlightenment that leads to finally the establishment of a successful product and productivity in a fabrication. On this slide, there's lots of technologies. Just one remark that I wanted to write, even several technologies on the same position on the slope can still have many much different time scales until one can expect maturity on this level. But I don't want to dwell on this. I just want to show you that terahertz had gone through the same thing, at least from my personal experience. And although terahertz is not just one technology, right? I want to focus here on terahertz imaging, where I have quite a bit of experience, at least for the German system. After in the 80s and 90s of the last century, right, the Austin switch, the photoconductive switch, the time domain spectroscopy, and then terahertz imaging build up large expectations. They actually reached a peak when people showed that you can take images through teeth, can images of cancer, and there was a big hope and expectation that terahertz could be used quickly in medical applications. However, then turned out that this was all hyped up, and the frustration was very big. Then came 9/11. Now suddenly terahertz got again attached with a lot of hope. Now in this case for security imaging. So indeed, there's very successful demonstrations, for example, from Kinetic, the company in England, or JPL. This is an image that was taken 25 meters away through the clothes. People could detect hidden weapons. So it has potential. And based on this, then our German funding, Ministry of Science and Research, launched a big program. And again, was relatively disappointing, although this 100 gigahertz imaging system that I mentioned before from Rohde and Schwarz was one product out of this, but not for the higher terahertz frequencies where I'm moving. Now, where are we now? I think we are here somewhere on that slope where we realize what has to be done and what kind of potential, what kind of applications one might focus on. And now let me still, before I show you coming to the end later, then just another aspect of technology assessment, right? It's always difficult to make clear predictions. Most of you know this TRL scheme, technology readiness levels, right? From basic principles on level 1 up to a full implementation of technologies on the market at level 9. Now, in 2013, these people here made a technology assessment for the then existing mainstream terahertz technologies. And I want to just show you a few and make my comments on how successful were they with predicting. Well, for example, I think they were wrong with predicting this one. It's at a high TRL level, 7, 8, right? It should be already in a market. This was detection of explosives and related compounds. At the time, it looked very successful, but this is not a market that has developed out of this. Too many hindrances showed up. On the other hand, these other technologies that are assigned with relatively good TRL levels, they made it into markets, even though they are still small. I mentioned these technologies before. Another one where I think they failed is here, NDE. This is non-destructive testing. This was assigned a rather low TRL level, but this indeed is in a market, again, on a small scale, but is successfully used for characterization of materials and objects. So you see, not easy to make clear predictions that then can hold up to scrutiny later. When these three main obstacles that I mentioned, they only can be overcome by proper technology developments. And there is a lot of very important developments going on which can make one really hopeful. One important development that we also participated a lot in my group and with colleagues is to make detectors that are usable over the full terahertz range in mainstream silicon CMOS electronics. So this is examples of narrowband and a scheme of a wideband kind of detector. But beyond detectors, one has to go to systems on a chip, which you see in a title from a paper from the Pfeiffer group in Wuppertal. What they made in a chip is they combined a so-called spatial light modulators with a source in a detector, in an emitter array. That's actually shown here, right? There's a full array of terahertz emitters that can be individually addressed. Here they illuminate all at the same time. It's a far field radiation pattern, but each of them can be switched off off and on. And why is that important or interesting? Well, in terahertz imaging, there is a trend towards a technique that's called sparse imaging, right? Where you use only a single detector and illuminate your object now normally through such a mask as shown here, right? You change the mask pattern continuously and record your image then through this object with these different illumination schemes, and out of all these pictures, out of these single point signals that you take, you calculate back then how your image looks like. Now, until now, you needed a source and a spatial light modulator, but with this combination of these two elements in one source that can be individually turned on and off, each of these emitters in the array, this can now be avoided. It's a big step forward in a practical application. But then even one step further, not only systems integration should advance or advances, but also the technologies of specific applications improve a lot. So for example, there's quite an interest in three-dimensional imaging, which is a capability that terahertz radiation indeed brings in. So there's a bunch of technologies around nowadays, and I want to show you just one here from a Swiss group that is based on so-called tychography, sorry, a difficult word, that initially was developed in X-ray imaging. Now with coherent radiation, turns out that you can do 3D imaging, and normally it works that way. You have your coherent radiation, your object, but you illuminate only part of your object and move the object through the beam. And out of all these partial images and diffraction images, you then calculate back how your image looks like.
This is
now,
my moment
this
to tell
group here
Harmon
also,
that there's 5 minutes left.
Oh, I'm through in the next slide, I'm through. What they have done then is they put a fabric on top of the object and translate the fabric, use this as a scatterer. And out of these images that they get by scattering in the end, they derive both the amplitude signals, the phase signals, and even the detailed structure of this fabric that used as a scattering mask. This is what I meant, right? So you have a full advanced application technology in place that now combines technologies on the device level, on the system level with the specific application technologies. Now this brings me to the end. In this summer school, it will be all about discussing, presenting and discussing such advances on devices, systems, application technologies, and on the identification of suitable application scenarios that have been overlooked or not gotten as much interest as they should. And all that to help you, the young researchers, contribute to that research and developments at your best. With this, I welcome you too to this summer school and wish us a good exchange despite the COVID limitations. Thank you.
No, thank you to you, Professor Roskos, for your enthusiastic and motivational introduction to the science behind terahertz, but also to a glimpse of some of the successes, but also the glimpse of so much work and exciting work to do. So very inspirational. Thank you very much. This summer school, as just mentioned, is about science, but also is on the impacts and prospects for real applications. And connected to it is also about exploring possibilities for innovation, entrepreneurship, and strategic collaborations across academia, private, and public stakeholders. Now it is our honor to introduce Onno Hauskamp, who is a technology and international cooperation advisor at the government of the province of North Brabant.
Nice to see my own slides up, I think. I hope they are. Yes, thank you. Thank you, Ildefonso. This is, what can a regional government representative say to such a large and diverse group from all over Europe, I guess, and what can we actually offer? And in this case, I wanted to focus mostly on the, actually the application part and how to turn it into a business. This is not the goal of a summer school, but it can be. And this is something I wanted to focus on, because this was something we have, at least in Brabant, we have built out into quite a comprehensive ecosystem for support. So once you have established your idea, you have a proof of concept, and we have established funding mechanisms and support mechanisms. And the main support mechanism that we have, should you decide in Brabant to build up this idea and see whether it's viable as a startup, we very much encourage you to get in contact with the people from Braventure. They have main representatives all over the province, naturally also in Eindhoven, where most of the technology happens. And they can guide you through every step of the process, going from those first subsidies, so you can actually see whether your idea is viable, to very large funding rounds, which can go up to 10, 20 to 30 million. In the meantime, I think that this is mostly a very sterile message to bring, but examples usually work better. And in this case, I wanted to start out as a support mechanism for photonic startups, which is, I've been told, a related field. You'll have to excuse me, I'm more of an economics guy than specialized in technology. But for photonics, we've built up something called Photon Delta, which we as a regional government started up and helped with the national government to create a funding mechanism worth about 250 million. From that mechanism, we encourage a lot of startups. So one of those startups we helped build out was Smart Photonics. It's a pure play indium phosphide foundry. And they recently received 30 million funding round, actually straight from the government with the help of Photon Delta. Another one, Effect Photonics, which is focusing on communications system on a chips, and they actually used the foundry from Smart Photonics, but they also did a 30 million funding round recently with the help of Photon Delta. Now, some more specific startups in the terahertz environment in the Netherlands is Terranova, which is actually based here in Eindhoven, and Dutch Terahertz Inspection Services, which is based slightly towards the north, but well, the Netherlands is quite small. And in this case, we try to encourage you to gain your ideas and build them out. And I wanted to capture that in several pictures. And this is also the message I wanted to give you going into your summer school. First off, I tried to find a picture of a scientist having fun in his laboratory. And well, this is quite hard a picture to find. But so one of the pictures that always came up was Nikola Tesla in his lab with trying to conduct electricity through the air and transport it in a way. Now, I know the experiment was quite serious, what he was trying to accomplish, but I'm pretty sure he had a lot of fun. And this is also something that I wanted to wish for you in this summer school in the coming days. Secondly, I hope, and this is something that is quite hard in these times of COVID, but I hope that this summer school will allow you to exchange ideas and collaborate with them. Please remember that if you plan a startup, you can have a good idea, but a good idea alone will never blossom into a company. You will have to bounce off your idea to others and share your idea and create a team. We found that this is pretty much the only way to really build out any idea into a company. So share, bounce off ideas, improve on it with others. This is something that we found essential, and is also something I wish for you to find in this summer school, even though it's largely digital. And lastly, it is to dream big. Apparently, it's now a dream of most billionaires to go into space. But I know for a fact that Jeff Bezos of Amazon has dreamed of this since the late 90s. Well, it only took him 25 years to build a company that allowed him to spend as much to build a new company called Blue Origin and go there. So also, even though what I've been told, terahertz is quite a small wavelength, think big, and try and find that next good idea. So from the regional government's perspective, I hope to see eventually some of you participants as new startups in our province or elsewhere in Europe. Thank you.
Thank you very much, Ono, for your sharing with us your experience and for your encouraging and motivational talk on the power of collaborations, but also about the different schemes available in the province of North Brabant to make your dreams reality. So thank you very much for your support. And with this note about learn, collaborate, and innovate, I declare the 2021 Summer School on Terahertz Technologies and Applications opened. Thank you, and to all of you who are watching us live. This session will be closed, but for the registrants, we will continue our program. And in that note, the continuation of our program is with the first keynote lecture, which is going to be presented by Dr. Peter Haring Bolivar from the University of Siegen in Germany. So, Peter, the podium is now yours.
So, Ildefonso, I hope audio quality is okay?
I hear you very good.
Okay, perfectly. So it's a great honor to be part of this very interesting meeting. And before I go to the start of this conference, I would really like to congratulate the whole team at Eindhoven. This is a copy of a kickoff presentation of